see me clearly now?
Yes, sir.
Thank you.
Yes, sir. Amos, sir?
Sir, yes, sir.
Yes, we will start at 10:05, sir.
All right, all right.
10:05,
Okay, sir. 3 minutes more.
Yes, sir. Actually, 12 participants have joined now.
Sir, I informed to principal.
Yes, sir.
They also ready to join.
Yes, sir. Very good, sir. Yes, sir. Amos, sir.
Yes, sir. Shall we start, sir?
We'll start, sir.
Okay, sir. A very good morning to one and all. Your assumptions are your windows on the world. Scrub them off every once in a while or the light won't come in. This is a quote by Isaac Asimov. So it is our time to brush up and refresh ourselves. Welcome to the AICTE sponsored 1-week short-term training program on fundamentals of FEA and its applications in engineering, organized by the Department of Mechanical Engineering, Panimalar Institute of Technology. On behalf of the Department of Mechanical Engineering, Padmanabhan Institute of Technology, I welcome you all for this inaugural function of the short-term training program on fundamentals of FEA and its application engineering. Now, I request Dr. N. Nityanandan, Head of the Department of Mechanical Engineering, to deliver the welcome address.
Very good morning to all of you. I am Dr. N. Nityanandan, Professor and Head of Department of Mechanical Engineering. This is wonderful occasion we are gathering here. I really thanks to the AICTE and our management giving this opportunity to welcome and invite all our participants to this STTP program. This short-term training program, Fundamentals of Finite Element Analysis and its Application in Engineering, is organized by Department of Mechanical Engineering, Panimalar Institute of Technology, which is approved and sponsored by AICT and others supported by our management. The finite element analysis is a numerical method for solving problems of engineering and mathematical physics. It is a computerized method for predicting how to protect the product react to the real world forces, vibration, heat and fluid flow, and other physical effects. Finite element analysis shows whether a product will break, wear out, or work the way it was designed. This FEA used in different fields like structural analysis, solid mechanics, dynamics, thermal analysis, and electrical analysis. This program has been conducted in 3 phases. It is my great pleasure and honor to invite our chief guest, Dr. Padmanabhan Krishnan, Professor, School of Mechanical Engineering, VIT University, Vellore. Welcome, sir.
Welcome. Thank you so much. Thank you so much.
Thank you. Welcome, sir. And I am very happy to welcome our principal, Dr. T. Jayanti, ME PhD, to this inauguration. She always gives the maximum support and guiding us in a proper way. Welcome, madam. And also, I extended my warm welcome to the participants from various institutions. And definitely this program will educate in your profession, because the short-term training program is aimed to enrich the knowledge of faculties through the interaction with the eminent personalities from industries and academics. The knowledge sharing will improve the teaching learning process to the students and benefit the society also. I hope everyone will take the result of this program and make this event will get grand success. Thank you.
Thank you, sir.
Thank you.
Now I request Dr. R. Murugan, the coordinator, to introduce the chief guest for the occasion.
Good morning, everyone. I am Professor R. Murugan. So it gives me immense pleasure to introduce my guru, Dr. Padmanabhan Krishnan, for this occasion. I'll read out his brief profile. Dr. Padmanabhan Krishnan took his BSc degree in physics with the first class from the Madras Presidency College in the year 1984. He then took his MSc Physics with Material Science from the Annamalai University, Chidambaram in the year 1986 with first class. He then proceeded to secure MSc Engineering and PhD Engineering degrees in the field of fiber reinforced composites from the Department of Materials Engineering from Indian Institute of Science, Bangalore in the year 1991 and 1995 respectively with distinction. Prior to that, he had his work experience in the area of high temperature ceramic superconductor and silicon semiconductors. After completing his PhD engineering, he was a visiting scientist to the National Aerospace Laboratories, NAL, Bangalore, in their prestigious HANSA all-composite aircraft program. He has been a postdoctoral fellow with the NSTV, Nanyang Technical University, Singapore, a guest researcher with the University of Delaware, USA, a guest faculty at Comtech, IIT Madras Composite Center, IIT Madras, and a research fellow with the Innovations in Manufacturing System Technology Program of Singapore Massachusetts Institute of Technology, Alliance, Singapore. He joined the Department of Mechanical Engineering, Sri Venkateswara College of Engineering, Chennai in the year 2005 as a professor and was shouldering the department's research initiatives for nearly 5 years. Presently, Dr. Padmanabhan is a professor and till recently he was the assistant director of the Center of Excellence in Nanocomposites in the School of Mechanical Engineering at the VIT University at Vellore. His center secured high funding from government agencies and organizations. He has handled and successfully completed many prestigious and funded and consultancy projects to the tune of a few crores. He has more than 270 publications in international journals, international conference proceedings, project documents and reports in the area of composites and nano-composite materials and their design. He has also authored a textbook on Kevlar fiber composites and many book chapters. He is currently engaged in a few contracts for books and chapters with international publishers of high repute. He has recently filed for 3 patents on metal polymer composites, composite yard, and biopolymer based polymer composite encapsulants for electronic packaging. Dr. K. Padmanabhan is a Life Fellow of the Indian Institution of Production Engineers, Bangalore, Institution of Engineers, Kolkata, and the Indian Association of Structural Engineers, New Delhi. He is also a life member and a chartered engineer with the Confederation of Engineers. The Indian Society of Mechanical Engineers, Chennai, conferred the Senior Life Fellow status to him recently. In 2018, he has been inducted as an Indo-Malaysian Life Fellow of the Society of Innovative Educationalists and Scientific Research Professionals. He has guided 5 PhDs and is currently guiding many PhD scholars, master students and P.Tech students. I am also one of the scholars for him. Awards and recognition. He has been awarded many awards, so I will list a few. Innovative Technologist and Dedicated Teacher, Society of Professional Engineers in the year 2017. He received Best Professor in Mechanical Engineering Department, ISME 2017 and 2018 year. And he received Abdul Kalam Best Mentor Award at the VIT University in the year 2018 and 19. He received Albert Nelson Management Award in the year 2018. And he received Honorary President for ISME and SIE SRP in the year 2019-20. He was one among the 4 professors to file the Institutions of Eminence IOE application for VIT Vellore and secure the distinction in 2019 and many more accolades to his name. He is a sensitive environmentalist, an adept cricketer and a musician who is fond of history, traveling, wildlife and writing. So he lives with his wife in Vellore, India. So it's a great pleasure. We have Dr. Padmanabhan for our inaugural function. So I welcome our Professor Padmanabhan. Sir, welcome, sir.
Welcome, Morgan. It is a very glad thing to be hosted by my own, one of the best students I ever had in PhD. And I thank the coordinators of Panimalar Institute of Technology and Panimalar Group for the wonderful opportunity given to me, because I stand humbled when I am asked to inaugurate a nearly 3-phase extensive FEA program. Many conduct FEA programs for a day or two, even some of the software companies who sell software normally conduct their training session for a day or two or maximum 3 days. But here is an institution that is doing a phase 1, phase 2 and a phase 3 that would go around like 40-45 hours multiplied by 3. That would be more than say about 120 hours of rigorous training in FEM. So like this is a very tedious thing, and then I congratulate you on my behalf and my institution's behalf for having done such a wonderful thing. And I thank AICT for sponsoring this, because I feel a part of this too, having been honored the duty of doing the inauguration. So thank you, Morgan. Thank you, HOD and the organizers of Panimalar for the wonderful invitation. Yeah, we all need no introduction to FEM, as most of you are faculty colleagues junior or senior or sometimes even exact colleagues. So, finite element methods actually came into being in the late 40s and early 50s, and then I'll be telling you about it in my first session. What we really like about finite element methods is that it does away with testing, and then it really saves you cost. The speeder the computer is, the faster or speeder the computer is, we are really having a wonderful time trying to kind of get very near to the analytical solutions of the values. So FEM now has grown or matured into very fast analytical platforms, analytical softwares, and then analytical formulations. So in my lecture later, like I will be talking to you about a very different aspect of how to pay importance to formulations, techniques, what techniques are available, and then how to pay importance to solvers. So I'll be concentrating on that, and I thank Murugan for the wonderful introduction having given to me, but I feel that the introduction was slightly too lengthy, and then I don't deserve it, and then it could have been a little shorter, but well, thank you so much. So I wish you a very great phase 1, phase 2, and phase 3 session, and I also wish you a lot of interaction, and I think that phase 2 I might make a comeback with some inputs on finite element methods in manufacturing, because people are trying to simulate manufacturing better now that we have a lot of tools like additive manufacturing and then many other techniques and the latest digital printing and all that. FEM is kind of diversifying into a very important tool. And the way it goes, FEM would be equal to the non-destructive evaluation techniques, because you don't need to test without doing, at least in NDT, what you do is you need a post-fractured specimen or a fractured specimen. Here you don't need even that, and then I'm sure that one day we will have a very high degree of reliability if you are able to formulate for all the material systems and understand all the materials and advanced and smart materials better. So I once again wish you a very happy FEM session, phase 1, phase 2, and phase 3. And thank you so much for having invited me. So I thank you, and then I conclude my inaugural speech, and then I declare the phase 1 open. Thank you so much.
Thank you, sir. Thank you, Professor. Amos, sir?
Yes, sir. So, dear participants, we'll resume the first session after 5 minutes. So, you can just stay online and we'll resume the first session in a short time. Thank you.
Thank you.
Dr. Murugan?
Yes, sir.
I think I have to press present now and then put my presentation.
Correct. Yes, sir. Yes, sir.
Yes, sir.
So now it says tab, it says window, it says entire screen. Which one?
A window, sir.
Window. Okay.
And then just open your PPT, sir. Your PPT.
Okay, thank you.
Yes.
I think I have to put it in the desktop first, right?
Yes, sir.
I need a shortcut.
Yes, you have to open the PPT at the back end.
Okay. Okay.
Sir, are you able to share the screen, sir?
One minute.
Yes, sir. Yes.
1 minute. I think I'll have to create a desktop shortcut and then open it from the desktop shortcut. Give me 1 or 2 minutes.
Yes, sir. No problem.
Can you see?
Yes, sir. Clear, sir.
You can see?
Yes, sir. Yes, sir.
You can see the title?
Yes, sir. Introduction to Design.
Okay, thank you.
Yes. Can you go on full screen,
Okay,
sir?
so,
Full screen.
pardon?
Full screen, sir. Can you put it on full screen?
yeah, I'll put it in the slide mode.
Yeah, yes, sir. Perfect, sir. Thank you.
Is it okay now?
Yes, sir. Perfect, sir.
Yes, sir. Slide is visible now.
So, can I begin?
Yes, sir. You can start.
Okay, so a warm welcome to all the participants. I hear that there are about 30-35 participants. It's a good number, considering that it's a very narrow field. Even most of the mechanical engineers do not study FEM. In some of the institutes like ours, we have FEM as an elective, not as a core like in Anna University. Well, so like as I'm the opening batsman, I have a lot of responsibility like Tendulkar or Sunil Gavaskar or many others. So like I would like to give you a very different idea about FEM. Not generally kind of open the topic and then tell you how to press a button and then constrain and then what kind of techniques are available and then how to solve the structural problems. So I'm not going into that. Though my title says Introduction to Design with a different element, finite element approach and applications to engineering problems, I would be looking at first a brief introduction to FEM. So the brief introduction is about a very basic definition to FEM. I mean, I don't have to, but as I told you that I've been asked to kind of inaugurate and then deliver the first lecture, like I would just like to warm up those who are kind of getting back into FEM after some time. So the numerical method used for solving problems that cannot be solved analytically is what we refer to as the finite element method. Finite difference method, on the other hand, is pretty simple because you cannot do complex geometries and then you have to do simple geometries, and you get a solution very fast and you get an answer quite easily. So finite element methods is slightly for more complicated geometries, different kind of materials, composites, smart materials, and so on, and is well suited for computers which are not simple basic computers. Originally, it can be applied to problems in solid mechanics. It was applied to rather problems in solid mechanics. And there are other application areas which include heat transfer, fluid flow, electromagnetism, and so on. So finite element method basically is about the pre-processing, solution, and post-processing. So it's just the single slide that I'm giving you where you are going to look at geometry, how to do geometry, how to model the analysis time, and what material properties to give, and how do you go about meshing, and what would be the boundary conditions that you adopt or the boundary conditions that you give, and solution, like how to choose solvers, how to solve linear or non-linear algebraic equations simultaneously to obtain nodal results, like the displacements, temperatures, and so on. And after solution, we are looking at, after displacements and temperatures, we are looking at, say, post-processing. We obtain results like heat flux, stresses, or direct results. That refers to post-processing. In some of the modules, post-processing might be a slightly tedious thing because you have to adjust color contours to suit your domain of interest, or you've got to exactly map it with stresses, whether plastic or elastic, and so on. Well, so I hope that I make a blurred picture clear, or clearer. The first picture that you see is quite blurred, and then even in basics, I decided that I will not talk about any manufacturing simulation or any serious thing about sandwich composite or smart material simulation, but this being the first lecture, I thought I would go by a very simple, effective technique to do formulation and how to use symmetry and mathematics in your formulations. Because that is very important. You have to be a mathematician first. Though, like if you work on workbench or say other things, you don't need to know much about formulations or read even an element library. So it will give you a choice, this or that. So let me try to make the blurred picture here. So like Swami Vivekananda said, the duty of a teacher is to make his students, the duty of a teacher is to make his students think and not just learn. So I would try to make you think and then not like kind of go for a class. Right? Yes. I thought I would just show you a slide of how it all began. History of finite element analysis and finite element analysis, or FEM, goes back to 1943 when Coulomb, who utilized the Ritz method, the Rayleigh-Ritz method or the Ritz method of numerical analysis and minimization of variational calculus. Right, you just write dou something by dou displacement. You're trying to minimize it to zero and so on. So this was the first principle that was used in 1943. 1943 was a time when the Titanic tragedy was about to be unraveled because of DBDT, and the Liberty ships and the other ships were kind of being held in the cold waters or frozen waters, and then they were not living up to the World War standards. So like the first paper around that time was out in FEA. So I'm just giving you some kind of understanding of the time frame. A paper published in 1956 by M.J. Turner Cloud published in 1956 by M.J. Turner, Cloud, Martin, and Tom, established a broader definition of numerical analysis. The paper centered on the stiffness and diffraction of complex functions. So Argyris, Barthes, Zankiewicz, Jane, Reddy, and then one of my own gurus, Datta Guru, who is actually a student of Argyris, they followed suit. By early 70s, FEA was limited to expensive mainframe computers, generally owned by aeronautics, automotive, defense, and the nuclear industries. Since the rapid decline in the cost of computers and the phenomenal increase in computing power, FEA has been developed to a very incredible level of precision. Well, a piece of history from fighter jets. So during the Second World War, actually the Germans were the first ones to come out with jet planes. So these were invented late during the 1944. They were kind of late into the war, and then they could not win the war for Germans. But they were totally unaware of aeroelasticity, FEM, structural mechanics, fracture and failure mechanics, and full-scale fatigue, composite materials, computational fluid dynamics. And then smart materials. So they did not know all these things. There were no FEM, but it still flew. And flight was not too comfortable, but it still flew. So initially the cart was put before the house or the hall. They did not do it methodically. Like they did not do CFD, aeroelasticity, structural nonlinear mechanics or linear mechanics, assembly, and they did not know even the ductile metal transition properly. It was just trying to get out of dynamics. So essentially they put the cart before the horse or the ox, and then you see an ass there sitting there saying forward. It was not too forward. So you are rated by what you produce, not what you are tempted, right? Well, so now let's just take a look at nature and symmetry. Like, as I'm a nature fan, I would get into some of the things that nature has taught us in symmetry. So the sunflower has a radial symmetry. In FEM, you know, you need symmetry, quarter symmetry, half symmetry, or say quarter symmetry, half symmetry, or you need full symmetry, cyclic symmetry, or symmetry in a particular pi of a kind of a big pizza. So sunflowers boast radial symmetry and an interesting type of numerical symmetry, which is known as the Fibonacci or the Fibonacci sequence. The Fibonacci sequence is 1, 2, 3, 5, 8, 13, 21, 24, and so on. So what you do is you determine it by adding the two preceding numbers together and get another number. So the leaves tell you about bilateral symmetry. The leaves tell you about bilateral symmetry. So like you get what is called an exact bilateral symmetry in a spine, or you can have a glide plane symmetry where the left spine is a little away and then the right spine takes over from the main spine a few millimeters away, and then you have the other one. So the first picture is glide plane symmetry, and the second picture to your right, top right is it is bilateral. if you look at the other types of symmetry, mostly they are biplane or glide plane symmetry. Even flowers have some kind of strange symmetry that you can use in drawings where you have a shaft and then turbofan blades and then so on. So nature gives you a lot of inspiration to study its symmetry and adapt it into any system that you want. Hypogynous, perigynous, epigynous, and so on. So hypogynous is where you have the ovary, which is inferior. So in perigynous, compared to the hypanthium or the ovary, you have some kind of a equal distance, and then you have an inferior. Sorry, I think I missed it. Like hypogynous is where the ovary is superior to the petals. In epigynous, it's inferior, and then in perigynous, you have an ovary that's exactly at the same level as hypanthium. You have polysepalous, multiple petal flowers. The gamosepalous, united sepals. You have only one sepal or one petal sometimes. That is gamo, united. So how would you model a gamosepalous flower? You can model it with 360-degree rotation where n is equal to 1. Where n is equal to 1. If it is 180 degrees and then you have two kind of things, n is equal to 2. Then for 4 petals, where you have like the Deming cycle, you have planned to check kind of segment. Then it is a case of n is equal to 4. In polypetalous or 4-fold or 5-fold or many-fold flowers, you have what are called symmetry operations. In gamopetalous or united, the gamopetalous or united scales, you have what are called united flowers, or where the symmetry is n is equal to 1, and then you go for a 360-degree single petal. Then just use terms like periodontal, epi, ortho, prosto, and endo and dendrocytes. It's all an inspiration from nature. Well, now let's look at a very different kind of a symmetry that's very important to material systems. Because if you need to model, you need to know symmetry very well. World's biggest flower has 5-fold symmetry. Like you see the botanist measuring the diameter of a Rafflesia flower. This grows a lot in the Southeast Asian range. This grows a lot in Southeast Asian range. So in the Southeast Asian range, this Rafflesia flower grows. You see the botanist Jamelinais measuring the diameter of a Rafflesia flower. It's a single flower with 5-fold symmetry, where n is equal to 5, and the whole flower is about nearly 1 meter in diameter. And it doesn't grow in many other, even in India you don't get it. You get it only in ASEAN, or the Association of Southeast Asian Nations. So, in quasi-crystals, you have 5-fold symmetry, like chromium, magnesium, zinc quasi-crystals, you have 5-fold symmetry. You have chromium, magnesium, zinc quasi-crystal 5-fold symmetries, which are ordered, but not periodic. You don't have a periodic ordering, but you have a 5-fold symmetric ordering. If it is totally periodic and ordered, well, wonderful. Like you wouldn't have had a 5-fold symmetry. Just think about it. Starfish and sea urchins again have n is equal to 9. It's a very odd thing. So you have n is equal to 5. Normally people, the mechanical engineers don't use n is equal to 5 or n is equal to 9. They use 1, 3, 16. Or they use 2 or 4 or 6 even. But in fan blades, you again don't use odd numbers. Normally you use even numbers, because you need to have a symmetry and you need to model it and so on. But starfish, sea urchin, and the bifold symmetry flowers and quasicrystals are rarities. So if you're modeling them, you need to understand symmetry first. Then comes the Nautilus or the spiral symmetry. In addition to plants, some animals like the Nautilus exhibit the Fibonacci or the Fibonacci numbers. For instance, the shell of a Nautilus is grown in a Fibonacci spiral. The spiral occurs because of the shell's attempt to maintain the same proportional shape as it grows outward. So it maintains some kind of a diameter scaling, cross-sectional perimeter scaling or diameter scaling. So this is the shell's attempt to maintain. Now, if you want to do, for example, like you want to model a Nautilus and then understand its mechanical properties, like by giving, constraints and then all that, I start with nature. It's grown as a Fibonacci spiral and the spiral occurs because of the shell's attempt to maintain the same proportional shape as it grows outward. So in the case of Nautilus, this grown pattern allows it to kind of grow in a very proportional manner about its whole life. So unlike humans, who do not have this kind of a Nautilus spiral symmetry. Now, in faunal bilateral symmetry, where you can get humans or tigers or butterflies, it's all bilateral. So the peacock's bilateral symmetry is again a wonderful thing for you to model. Now there is a very strange kind of symmetry called push-pull symmetry. Okay, let us say you have a mirror, and then the mirror has a circular hole. Okay, and you're pushing a goat into that hole. His hind legs are behind the mirror. You cannot see it, and then his torso is exactly fitting the hole that you have made in the mirror. So what you see is the goat with its two forelegs and the torso, half torso, and the face. Now, if this goat decides to move out, in the mirror what you would see is the goat moving the other way. So the goat can push and pull itself with a mirror symmetry. Okay, this is called the push-pull symmetry. Now there are some conditions in real life where you have what is called a push-pull fatigue. So you have a push-pull fatigue, right? Well, and my PPT is all fully occupying the screen. So otherwise, if it is a class, I would have acted it out with the whole play. In push-pull symmetry, or in push-pull fatigue, let's say. In push-pull fatigue, what happens is sigma is not twice that of tau for an isotropic decay. Sigma equals tau. If whatever stress you get that under some conditions the push-pull fatigue cycling, you get sigma equals tau. Shear stresses can be phenomenally high. So push-pull symmetry is also one rare symmetry that you can use effectively. Or let us say you are looking at something coming out and then going, like something trying to jump out of a well and then going in, and then you have water in the well, and then you see the other side going down and then up and then so on. Or let us say you have a mirror and something is coming out of the mirror, and when it comes out of the mirror, when you go back, you're going further into the mirror. Okay, so you can use this kind of a mirror symmetry in order to understand a lot of systems with a perfect mirror symmetry. Now, near perfect mirror image of Milky Way is what we are going to experience now. The Milky Way is not like the Nautilus. As we have seen, symmetry and the mathematical patterns exist almost everywhere we look. But these laws of nature limited to our planet? Apparently not. Having recently discovered a new section on the edges of the Milky Way, Milky Way galaxy, astronomers now believe that galaxy is a near-perfect mirror image of itself. Now, for the solar system to go around the Milky Way, having recently discovered a new section, so we have a near-perfect mirror image of itself. Now let's go into nature and mathematics. Before understanding maths, you must know one thing. The brain has a reptilian area where you don't do much of maths. Okay? Middle brain, where you are capable of very elementary maths, like you can identify the moon and then the moon and the sun if they are dual. And then the new brain, the neocortex. Now the neocortex is capable of FEM, finite element. In the left brain you have logic, analysis, sequencing, linear analysis, mathematics, language, facts, and then think in words, or say words or songs. Words or songs, or think in words or words or songs, or computation skills. So mostly FEM requires left brain. But if you think that you require only the left brain with some neurotransmitters or right brain, you are wrong. You require creativity, imagination, holistic thinking. Like how can you break it into simpler parts and then it can be assembled later, or where you can infer through proper scaling, connection, or a spiral symmetry operation. Our post processes are pretty limited. Like if you think about it, you'll come to all sort of wonderful conclusions. Intuition, arts, rhythm. Now, if you're doing vibration analysis and mode separation as a musical instrument, modeling and simulation, you need the right word. Non-verbal, understand. So, and then feelings are right brain. Visualization, like FEM is all, right? Formulation and visualization. So you need a lot for FEM. Good FEM operators normally are good with their left brain and right brain thinking. Tune of songs, then daydreaming. Like one type of daydreaming is to make a jet plane, as they made in 1944. You didn't think of FEM. But now in FEM, let us say you daydream, because you're trying to connect non-destructive testing, actual sonar, or say ultrasonic testing, sound imaging, or say sound testing, with finite element vectors. Okay, like I have something, sound travels in it. I want to model, simulate, and then simultaneously with the sonar apparent, I want to check what would be the wave propagation. What would be the wave propagation? Now, how would the stresses develop? Can I model it at the same time, watch it in sound testing? That would be a beautiful coupling. Not many have done that, right? Visual Max, FEM, SVG, Scalable Vector Graphics, Mathematics of Graphics, Lyrical Music, Quantitative Pattern Recognition, Modular Assembly are all demanding on both sides. Now, all these things require Visual Max or FEM or Scalable Vector Graphics or pattern recognition or modular assembly. They are demanding on both sides of the brain. You require a Pacca neurotransmitter. You have to be alert. And some of them are even ambidextrous. I mean, they can kind of move the mouse because you are compelled to move the mouse with your right and then type with your left. So you become ambidextrous. So, right brain thinking governs left hand, left brain thinking governs right hand. Now, coming to what is required, like you need a kind of a brain-based approach for FEM. So that is a lesson that we learned from biomechanics. Division and multiplication began with mitosis and meiosis, and cell division and duplication. We learned division from mitosis and meiosis, cell division and duplication. Well, so the order of equations in nature should also be noted down because you have to formulate well. You're not only solving linear problems, but you're also solving linear problems, but you're also solving nonlinear problems, highly nonlinear problems, spiral problems, or turbulent problems. So the first exercise is Wein's law. In Wein's law, like you have the atomic and the nuclear emitted energy is proven to be a fifth power, like the five-space formula. Albert Einstein failed in his attempt to unify gravity with electromagnetism. He did fail. And then Kaluza and Klein proved that if space-time had a fifth dimension in which charge was the angular momentum in the fifth dimension, gravity and electromagnetism could be unified to general relativity. Now, why am I telling you all this polynomial laws and all that? In nature, you find everything. In mechanical engineering, you find just 3 or 4. Unless otherwise you're doing heat and radiation, you don't go to power 4. Stephen Boltzmann's law and all that. Otherwise, it is, thermite, linear, and then Lagrange. That's what we do. More equations are available. Like, for example, mass relationship or the heat generated in the circuit, then gravitation having a square root. So the area of the circle, quadratic polynomials. Now quadratic polynomials are Lagrange. So the volume is R cubed and then cube of side is A to B and C. Now mechanical power of swimming is proportional to the cube of velocity. If you are doing swimming model, biomechanics. Hermite polynomials all B, they are third order. Stephen Boltzmann's law. Stephen Boltzmann's law gives you the energy radiated per unit area, which is the fourth power of temperature. Now, what needs to transition from one stance or length to another, that increases with fourth power of step length. More or less true for human beings. Now, cylinder flow is again a steady flow around the buoyant finite cylinder within a rapid rotating core, which has a component proportional to the inverse V. So the laws of nature also give you what is called Brahms law, which is called Airy's law. The maximum mass of objects that may be moved away by a river is proportional to the sixth power of river flow speed. So if you are in CFD, you need higher laws. You know, you are going to start only at say 4 or 5, power 5. Sometimes for turbulence you need 7, 6, maybe more. Then van der Waals forces are proportional to the inverse 7th power of distance. So very short distance. Now, laws of nature continue where you are trying to calculate corrosion in river flow. Corrosion of iron and steels by acid river water is proportional to 7.5th power of flow velocity. Now, if somebody modeling corrosion, not just like an assembly or coupling or something, you can't do 7th power or 8th power. You have to do 7.5th power for the flow velocity. That would fit better for acid river water, where the pH is normally 2 or 3, or 2, 3 or 4. Jet noise. Now, Little's 8th power law states that the acoustic power generated by a jet engine is proportional to the 8th power of the jet. Laws of nature tell you that carbon flow from the ocean, that is from the upper ocean to the atmosphere, is proportional to the 9th power of the mass of carbon in the upper ocean. Stellar carbon cycle. Reaction rate is again kind of an energy generation reaction relationship. For fusion in stellar interiors in which hydrogen is converted from hydrogen to carbon, the reaction rate is proportional to anything from temperature power 13 in hot massive stars to T420 in stars like the sun. So if you are doing radiation modeling, or if you are doing cosmos modeling away from mechanical engineering, this is a lot. Exponential behavior, like the sound attenuation with unattenuated initial value of A0, where you get the attenuation coefficient K and then the distance of depth. So there you have the unattenuated initial value A0 and then the attenuation coefficient K and distance or depth E. Small k gives you a fit even close to the quadratic k, but large k will give you the fit that is very close to the exponential. In exponential functions itself, you can have small k and the large k values. Small k looks very much quadratic, right? Like taking. You can actually fit it very close. A0 into e4 minus kt, where you adjust k. You can get the value very close to quadratic, but not quadratic. the exponential growth is nothing but y is equal to AB power x, where b is greater than 1. In the exponential decay, y is equal to AB power x and b will be less than 1. Okay. Normally in ultrasonics, sound imaging, or in ultrasonics or in ultrasonic testing, we normally go for attenuation of the sound in a material. So this attenuation of the sound in material attenuates, right? So based on the attenuation, we get to know whether it is monolithic or porosities, cells, and so on. Now you must know what is called, you must be good in visual mathematics. So some CAD geometries can be drawn with just one or two equations, or Cartesian or polar, or say other kinds of parametric polar or parametric Cartesian equations. So the Devil's curve well, actually is some kind of an exhaust fan, like it is simply y squared minus y power 4 minus x power 4 plus ay squared plus bx squared equal to 0. Then you draw another equation that's kind of 90 degrees away. Then you get polar equation.
Now
you can also draw a Fermat spiral. So let's say you're modeling some kind of a spiral or rotary mechanism. Simple polar equation r squared is equal to a squared theta plus some line thickness definitions and the interspacing definitions would do for Fermat spiral. Formulation is easy. Like if you're not using ANSYS, let's say you're using MATLAB, this becomes very important. Now Lissajous curves, I'm sure that you have heard of Lissajous curves in sound. And there was a lady by name Agnesi. She was an Italian royal family lady. She lived slightly before Gauss. They had about 20, 30 years overlap. But she was popular 20, 30 years before Gauss. She had a particular distribution curve that did not look Gaussian. According to me, all the distribution curves began all the distribution curves began with the VIT University, where the y multiplied by x squared plus a squared is equal to aq. This particular Gaussian distribution which is not Gaussian, doesn't look like a Gaussian distribution. Actually, it can be fitted to some systems which are too brittle, where you have fracture and the fracture distribution. Polar equation for a Rafflesia flower. Let's say you're modeling the Rafflesia flower and you're trying to see the petal strength and all that. It's a simple polar equation. R is equal to A sin kb. Plotinian curves. And quadratics of the QPS, again I have another equation. Then hyperbolic spirals. Hyperbolic spirals have a particular kind of equation like R is equal to A by theta. Then we have polar equations which actually polar equations which actually read something like cos p is equal to AP cos p theta.
சாப்பாடு காரக்குழம்பு சாதமா?
So they are sinusoidal spirals. A point-based representation of the mathematical surface. Let's say you have a fountain. Let's say you're modeling a fountain and then a small pond. You can start with some equation like, z is equal to f of xy, where you have cosine root of x squared plus y squared divided by root of x squared plus y squared. Finished. And you can adjust 4 sine, 3 sine, or say other sines and xy values and get exactly a beautiful architecture. Now the FEA prerequisites are rather physics-based laws. So the first principles are Newton's laws. It's a body under external. It's a body under external loading. So the first principle is Newton's laws, where it's a body under external loading. And then you understand area moments of inertia, especially in beam equations. And then stresses and strains and stress concentration factors, principle of shear stresses. Stresses in states, then bending, shear, torsion, pressure, contact, thermal expansion. So these are all the prerequisites. Like you must have a thorough understanding of these things. Plus, a lot of understanding of the material properties, material linearity or non-linearity. Material properties, like you need a clear understanding of the material property, linear, non-linear, then electrothermal, smart, failure modes. You need to have a very thorough understanding of failure theories like psi U, psi Q, maximum stress, maximum strain, then Christensen, then other kinds of theories. Then there are dynamic analysis. Dynamic analysis is mode shape understanding, Fourier or Laplace transforms. So the FEA prerequisites are severely mathematical or demanding first principles understanding in physics. So let's say you're formulating element equations. Several approaches can be used to transform the physical formulation of a problem to its finite element discrete element. If the physical formulation of the problem is described as a differential equation, then the most popular solution method is the method of weighted distribution. It's called the method of weighted distribution. If the physical problem can be formulated as the minimization of a functional, then the variational formulation is usually used. So one family only a method used to numerically solve the differential equations is called the method of weighted residuals, where you have the approximate solution. You have the approximate solution which is substituted to the differential equation. Since the approximate solution does not identically satisfy the equation, a residual or an error sum results. So consider differential equation where kind of power 2x plus q equals 0. Suppose that y is equal to hx is an approximate solution. Substitution then gives dh, the double differential of x plus q is equal to r, where r is a non-zero residue. So like integrate wix rx equals 0. Like you know the error and then you just put a weight here. You know how far you are away. That's also possible. Like you can have a wix where the weighting functions and the number of weighting functions which equals a particular result that you want, where the approximate solution is obtained. Is another consideration, another case. So the theoretical basis also provides for an understanding of what is called the Galerkin's method. What is called the understanding of Galerkin's method. There are several choices for the weighting function. There are several choices for the weighting functions. So in the Galerkin's method, the weighting functions are the same functions that are used in the approximating equation. So the Galerkin's method yields the same results as the variational method, and then and it's applied to a differential equation. Applied to differential equations that are self-adjoint. So the MWR is therefore an integral solution method. So the weighted integral is called the weak form. Why is it called the weak form? It is called the weak form if you have higher orders of polynomials. Many readers may find it unusual to see a numerical solution that is based on an integral formulation, but it is possible. So it is called the variational method, which involves an integral of a function that produces a number. Each new function produces a new number, and the function that produces the lowest number has the additional property of satisfying a specific differential equation. Now you consider the integral, pi is equal to pi is, okay, fine. Integral d by 2, then second differential of yx minus qy, and everything into dx equals 0. Now you consider the integral. You consider the integral pi is equal to integral of d by 2 y power you consider the integral d by 2, then double differential minus qy equals b, then into dx equals 0. So numerical value of pi can be calculated. So the variational calculus shows that pi can be calculated given a specific equation, y is equal to f. Variational calculus shows that the particular equation y is equal to gx, which yields the lowest numerical value for pi, is a solution to the differential equation. So like there's a second equation, like again second differential d of x plus q is equal to 0 and so on. So in the theoretical basis, the so-called Rayleigh-Ritz technique uses a theorem of minimum potential energy within the potential energy being functional, where pi is to develop the element equations. Let's say you have Rayleigh-Ritz technique uses theorem of minimum potential energy, the potential energy being functional. The trial solution that gives the minimum value of pi is the approximate solution. So in other specialty areas, the variation principle can be usually found. Now, not many FEM courses teach you solvers. They do not teach you solvers. They do not tell you about direct or iterative methods. In FEM courses, you normally you just press the button and then allow a frontal solver or a direct or an iterative solver to do the work for you. But how is a solver able to solve how many degrees of freedom? Note, matrix, huge matrix systems, where it will be an 18 by 18 or a 40 by 40 or even a bigger matrix. Now, you need to understand solvers, and then my request to teachers is to understand solvers and then include them in the syllabus. Like you decide whether it is direct or iterative. Like Cholesky or Gaussian elimination. Direct Cholesky or Gaussian elimination. That's direct. Then iterative solvers like Newton-Raphson, predict the character and so on. They are again iterative. Then there are sparse solvers, sparsely distributed, equally distributed solvers, sparse direct solvers. Then ANSYS uses a lot of frontal solvers. Now, no FEM course teaches you solvers. What are the various types of finite methods available? We have the applied element method. Applied element method for AEM, then the generalized finite element method, which uses local spaces considering the functions which are not necessarily polynomials. So the unknown solutions ensure good global or local approximation. So like microscale problems, boundary layer problems, mixed finite element problems. All use what is called a generalized FEM. Then you have the polynomial variable HPFEM, where you have elements with variable size h and then polynomial degree p that are going to achieve exceptionally fast exponential convergence rates. So if you are looking at high degree of polynomials where the variable size h is allowed and you are looking at fast convergence in an exponential manner, then you can use this kind of a method. Normally you don't use a direct solver, but you use an iterative solver. So the introduction of the scale boundary FEM method has been one of the most profitable contributions in the area of numerical analysis or contributions in the area of numerical analysis of fraction mechanics problem. It is a semi-analytical fundamental solutionless method which combines the advantages of both FEMs and procedures and even boundary element discretization. But unlike the boundary element method, no fundamental differential solution is required for the scaled boundary finite element method. So like they normally use it in fraction mechanics where you have discontinuities, or say like or you have other kinds of crack problems, extensional problems due to discontinuities and so on. It is also semi-analytical. The SFEM, it is called the smoothened finite element method, or the SFEM, smoothed finite element method, is a particular class of numerical solution algorithms for the simulation of physical phenomena. It was developed by combining mesh-free methods with the finite element method. Now there are spectral element methods which combine geometric flexibility of finite elements and the acute accuracy of spectral methods. So spectral methods are the approximate solution of a weak form of partial equation, normally of higher order, that are based on higher order Lagrangian interpolation and use only with certain quadrature specifications only. Then you have mesh-free methods, discontinuous Galerkin methods, finite limit analysis, stretch the grid method, and then Lubiniak equation with an iterative method and finite element. Now let me give you a few examples. This coupled field analysis is very important. In coupled field analysis, we will briefly describe how to do a thermal stress analysis. Thermomechanical analysis. The purpose is to show you how to apply thermal loads in a stress analysis and introduce you to coupled field analysis. Now you can have thermally induced stresses like in hot engine parts. When a structure is heated or cooled, it deforms by expanding or contracting, and if deformation is kind of constrained or restricted, you can do a displacement constraint or an opposing pressure. For example, like thermal stresses are induced in the structure. Another cause of thermal stress is non-uniform deformation. Due to geometric nonlinearity, you can have non-uniform deformation. Another cause of thermal stress is non-uniform deformation due to different materials and different coefficients of thermal expansion and so on. So there are two methods like sequential or say direct coupled method. That is a slightly older style of naming it. Now like most of the methods are kind of direct with a few compromise statements. Older method is kind of very efficient. It can easily be inputted and it can be automated. Like it is very efficient when you do transient analysis. the efficient when running many thermal transient time points but few structural time points. Now you have newer method which uses only one element time to solve both physics problems. That's normally a bit difficult because the same element has to solve the thermal and the structural problem. You might not find too many elements matching your requirement. And true coupling between thermal and structural phenomena is again a necessity. It may carry unnecessary overhead for some analysis. But in the sequential coupled field analysis, you have to go with the transients or the transient conditions. If you're not understood transients well, don't do the sequential coupled analysis. You might kind of, when you do time step and all that, be very bad. So like you do a steady state or transient thermal analysis and then do a static structural analysis. The job name and how to name the jobs is also written. You can apply structural loading including temperatures from thermal analysis and then solve review results. So the direct method prepares a model according to the element description, and you can apply the structural and you can apply both the structural and the thermal loads and constraints to the model. Solve the review and both thermal and structural results. So the direct method usually involves just one analysis that uses a coupled field element type containing all the necessary degrees of field, thermal as well as structural. Now in the sequential method, you can have coupling situations which do not exhibit a high degree of nonlinear interaction.
Hello?
The sequential method is more efficient and flexible because it can perform the two analysis independently of each other. But in dialect, we need the same element. We need to understand
roll number login la
coupling, direct coupling. And the advantage is
நீ அக்கவுண்ட்ல போயிட்டு ஆட் அக்கவுண்ட் இருந்தா யூஸ் another account அதுல போயிட்டு ஒரு ரோல் நம்பர் டைப் பண்ணு 2017 PIT ஒரு நம்பர் டைப் பண்ணிட்டு அட் போட்டு pit.ac.in அதுதான் உங்களுடைய அது போட்டு உன் பழைய பாஸ்வேர்டு போடு உள்ள போய்டும் ட்ரை பண்ணு அந்த டொமைன் நேம் மாத்தியாச்சு சரியா சரிப்பா சரி ஓகே
conjugate heat transfer, fluid flow, and electromagnetic analysis. So in my case study 1, I am coming to the last 10 minutes of my lecture. I hope to wind up at about level 45. So like we have done a lot of microelectronic packaging. So the bill of material includes copper lead frames, gold wires for bonding, then a silver adhesive based epoxy foam die attach, silicon dye and epoxy mold composite phenolics, fused silica powder and then carbon black powder as the encapsulant material, we had to do electrical, thermal, and then thermal structural analysis. How much would it get heated because of I squared laws, Joule heating, in a conventional package? So the electrical thermal analysis is based on the I squared laws for Joule heating. So from the Joule heating you get the Joule heating or I squared laws, you have to understand how the encapsulant material gets heated, or the dies get heated, or the die pads get heated, or the wireframe gets heated. Now, electrical, thermal, and thermal structural analysis electrical, thermal, or the thermal structural analysis are performed with these things in mind. The heat that is generated and the temperature that you get is input into thermal structural analysis, get the stresses and strains, and then how much it bends or warms or width. So these are some of the results that we have done, like von Mises displacement, the stress intensity factors, in-plane shear stresses, and so on. So the case study 2, we have also done stresses and other types of stresses in the maxillary molars of the teeth. The macerated heavy chewing stress will be around 193 MPa in teeth. If you're chewing chicken bone, if you have good teeth, the stresses that are developed would be higher than what pure copper or aluminum is capable of when you calculate sigma y or the yield stress. So a composite restorative must withstand this factor of safety. Composite restorative must withstand this with an with the factor of safety and with constant hydrothermal attack. Tooth is a functionally graded composite with the enamel and dentin. So like you have to model the tooth with enamel, then dentin, then soft dentin, and then the root section and all. So in the maxillary molar, the occlusion stress can be about 2 to 3 MPa. That is the occluding, the side by side thing, chewing. So these were all modeled. In case study 3, we looked at the LCA or the light combat aircraft generator. So the study deals with modeling, analysis, and performance evaluation of 5 kilowatt DC generator. So the complete solid model of the generator with its axles was modeled using Proengineer, long time back. It deals with the structural analysis of a DC generator casing. We find the stress and deflection of the generator casing due to a load factor of 9G because LCA is capable of 9G pulls, to which it was designed. So the effect of vibration of the generator casing and hollow shaft with the mounting are investigated through the detailed finite element analysis. So the bending and torsion natural frequencies of the hollow shaft were estimated to find the critical speeds. Torsion frequency of the hollow shaft is about torsional and natural frequency of the hollow shaft are estimated to find the critical speed. So torsional frequency of the hollow shaft is estimated by considering the mass moment of inertia of the rotating masses. For critical speed analysis of the hollow shaft, it is considered as simply supported beam. For the hollow shaft, it's considered a simply supported beam with required masses and inertias. Then the influence of the critical speeds due to casing stiffness is found out analyzing the casing with the shaft group. So like we did a very serious model for the casing, and then the cross section of the model was pretty tedious. It was done at CVRDE by my students with proper assistance. So finally, when we see the maximum deflection at 9G, when the aircraft makes a severe 9G maneuver, the maximum deflection of the generator will be only 9.676 microns within the limits. The stress of about 6.756 MPa is much lesser than the yield stress of the material, so like it just passed the test. So the mode shape of the generator shaft also was corresponding to the flexural critical speed. Like 54,972 RPM using flexural critical speed of 54,972 RPM using solid elements with inverted approximation. So this is the mode shape corresponding to the flexural critical speed of the shaft, and that was also well within limits. Well, I recently completed a project in 2016, which was for the aeronautical development and then the development board. The project number is 1650. So the air and DB project number was 1650, and the design optimization of aerospace sandwich composite for strength and stiffness was done, and then there when we looked at the Poisson's ratio of the foam, depending on the density of the core foam that we use for the sandwich composite, we found that the Poisson's ratio was not linear. With an increase in the density, it decreased first and then increased because of certain deformation and then dislocation assisted mechanisms. So this Poisson's ratio of isotropic foam plastics as a function of density is a very serious thing. Many American papers or British papers or even Australian papers have simply assumed an increase in Poisson's ratio when the material turns from low density to above density. It is not true. So we found this out after proper measurements and then used it in modeling, and we could get reasonable levels of accuracy. I wouldn't say excellent. Reasonable levels of accuracy. We did design optimization. We tried to see what would be the phase shift. We tried to see what would be the phase sheet weight, two phase sheet weight compared to the core. Long time back, Froud had done an analysis in UT. The paper is entitled Your Sandwich Orders. So he said that if the phase sheet of both the phase sheets
studies that were shared were very informative and
are 2 times heavier than the core,
easily relatable,
then it is the best spring. And it is exactly equal to the weight of the core. It's best for stiffness. Now when we checked it for these composites, not for Peacock, but for foam composite, we found that actually the optimum was around 2.5, 3.5, and then it varied with density, it varied with volume fraction, it also varied with the thickness of the foam, because in thickness of the foam, you have what is called shear flow. You know what is called shear flow. The shear flow is nothing but the shear stress multiplied by the thickness. Okay, shear flow is nothing but the shear stress multiplied by thickness. If the thickness of the foam is heavy, then optimization rules are different. Even for a rigid.
Thank you for a wonderful insight.
So we had a 10 mm, 25 mm, 40 mm thickness. We found that they were not obeying fraud. So like, and I would say it's very specific. It's very dangerous to have a common, weight-based or density-based law for stiffness and strength optimization and standard form. That's my conclusion. So the conclusion would kind of be a bit brief.
Get it from an experienced person.
I think my lecture introduced
first session itself is such a great boom for
introduction
us.
to finite element analysis to the audience.
Thank you so
and then
much.
The basic. Then the basics, the different approaches, formulations, and solution methods we outlined.
Different types of FEMs and FEA and whatnot. Thank you so much for your wonderful session.
So the emphasis was laid on solving structural, mechanical, and multiphysics problems. Understanding the material behavior that is a prerequisite to the correct modeling of the problem was also discussed. Some engineering applications of FEA approach as investigated were illustrated for the benefit of the FE society, and I think I enabled you to appreciate the depth of the subject field and take it up as a career. You need to be good in maths, physics first principles, formulations, then understanding symmetry and constraining well. And then you must understand not only constraints and then proper symmetry operations, but also understand solvers and the max of solvers. And post-processing is relatively easy to almost do. So Purnamada Purnamidam Purnat Purnamudashyate Purnasya Purnamadaya Purnameva Vashishyate. Sorry. Purnameva Vashishyate. From infinity is born infinity. When infinity is taken out of infinity, only infinity is left over. Sky is the limit. So is the blurred picture clear about your basic understanding of FEM? Because I didn't want to go into XFEM, extended FEM for fracture mechanics, or say borderless, boundless, meshless things and all there in the first lecture. So I was trying to tell you to be natural, to be brain-based, to be left and right. So I'm trying to put a few things clear. So thank you, and any questions, please?
Thank you, Professor, for your wonderful session. I think you have given an overview about finite element method. Participants, if you have any question, you can ask question with the professor.
Any questions? I'd be glad to answer.
Participants, if there's any questions, you can post it in the chat as well. I can read it out, or else you can unmute yourself and you can ask the questions. Okay. Thank you for your wonderful insight about role of FEA in modeling, simulation and machining, sir. The case studies that were shared were very informative and relatable. Thank you once again. And on behalf of Department of Mechanical Engineering, Panimalar Institute of Technology, and principal, HODs and all the staff members, we thank you for this wonderful session, sir.
Thank you so much. It's an honor to have given the inaugural address and the first lecture. Thank you so much, Panimalar, for your wonderful organization and the wonderful audience. If there are any questions, please you email me. Dr. Murugan knows my contact, and then I would love to chat with you as a time. Thank you.
Thank you, sir. Thank you very much.
Can I sign off?
Yes, sir.
Yes, sir.
Yes, sir.
So, dear participants, we have our next session at 2:30 p.m., which will be given by Dr. R. Murugan, Professor, Department of Mechanical Engineering, Panimalar Institute of Technology. So, the login will be the same thing, and we request you to log in at 2:30 p.m. today. Thank you so much for joining us.
Thank you, Amos.
Thank you, sir. Thank you.
Participants, please fill the feedback form for every session. It is a requirement, so don't forget that.
The feedback form is available in the chat. I'm resharing the feedback form now. Kindly fill it up. You can leave the session as after you finish the feedback form. I request everyone to fill the feedback form. It is available in the chat. So the next session will be at 2:30 p.m. Request everyone to join in at 2:30 p.m. Dear participants, after completing the feedback form, you can leave the meeting and you can join back in at 2:30 p.m. I request everyone to fill the feedback form. For every session it is mandatory, so kindly fill up the feedback form.
Amos?
Yes, sir. Yes, sir.
Sir, at 11:55, we can end the meeting.
Fine, sir. Okay, sir.
Okay.
Dear past participants, last call. Kindly fill up your feedback link. It is available in the chat. After filling it up, you can leave the meeting and join back again at 2:30 p.m. Thank you all for joining us. And we'll see you back at 2:30 p.m.